All right, gang, afternoon here. I did grade the tests, so what I want to do is go through it real quick. And then we can talk about lines in 2 and 3D, more general equations, and then we'll see if you have questions about anything. So on test 1 here, we had first question, it's not till 3:15. So, okay, first question was one of these conic section problems. So make sure you know how to do these. They will come back in a few places here. Okay, so we've got the x squared, and that's fine. We have an y squared and a y, so there's going to have to be some completing the square in there. We want to write this one as 3 times x minus 0. See the center? The 2 can be factored as y squared minus 6y. Leave a little bit of space. And then the 6 we can move to the other side. So for right now, it's just regrouping a little bit, just like we did in class on all of these. We need to complete the square. So to complete the square, we need to take half of the 6, square it, we get 9. But everything in there is multiplied by 2, so sort of technically we've multiplied this 9 by 2. So we've added 18. So if we're going to add 18, we've got to add 18 to the other side as well. So we'll have 3 times x minus 0 squared plus 2 times y minus 3 squared equals 12. And we're almost there. We want to get a 1 here, so let's just divide by 12 to get the 1. If you divide 3 by 12, you get 4, of course. Divide 2 by 12, you get 6, so it's y minus 3. So it's x squared over 4 and y minus 3 squared over 1. So this is the equation of an ellipse. And we just need to go through and find all of the characteristics about it. The numbers, this should be a 6, not a 2, sorry. The numbers underneath are squares of numbers. The book is calling them A and B, but I think it's just easier to think about it as how far left and right you go and how far up, down you go. So left, right is going to be plus or minus 2. Up, down is going to be plus or minus square root 6. And the center is at 0, 3. You can get that from the equation. So up here at 3, we'll see if that's too high. That's 3. Then we got to go 2 units either side, maybe about there. So 2. And square root 6 is around, I don't know, 2.5 or something. So we're here and here. These will be the vertices. So this vertex is at 0 and then 3 plus square root 6. And this vertex down here is at 0, 3 minus square root 6. And so the major axis is vertical on this one. So it sort of opens close. It's a sketch. So those are the vertices. To get the focal points here, the formula in the book, which we were allowed to use, was that if you took, you wanted to get c squared, that would be 6. And since it's a plus in the formula, it's minus. And you have to subtract in the right order, or else you get a negative, and that doesn't make any sense. So c is plus or minus square root 2, which is how far up and down you go in order to get to the focal points. So that focus is at 0, and then you go up 3 plus square root 2, and that one is at 0, 3 minus square root 2. And finally, I don't know where to put it in here, eccentricity is always defined to be the distance from the center out to the focus divided by the distance out to the vertex. And if you're can't remember which one it is, you know for an ellipse it has to be less than 1. So we have square root 2 and square root 6. So square root 2 divided by square root 6. So 1 over square root 3 or square root 3 over 3, which is certainly less than 1. around 0.6-ish or so. But anyway, so that's all the pieces. It's an ellipse. We have the center. We've got the vertices, the focus, the eccentricity, all of that. If you did make a mistake and then divide through here, I did try to follow it through as much as I could. Send me maybe a note, either in, maybe an email would be easiest. If there's some mistake you thought I made or want me to recreate something, you can do that. So that's that one. 2 is this curve. Cosine, I'm going to write it like this, just cosine t cubed y is sine t cubed. And so you just need to plot a bunch of points, basically, and realize that it starts at 1 and ends in 1, but it's not a circle. It definitely curves up like that. This was part of something called an asteroid, not asteroid, but asteroid. And later on in part C, you're going to do the corresponding tangent line at pi over 4. And pi over 4 corresponded to that point right there. At t equals pi over 4, x will be, you plug in the bounds. This was technically in part C, but I'm just going to do it right here. Part of it anyway. I get the cosine of pi over 4, which is square root 2 over 2, and that's cubed. And y is also square root 2 over 2, and it's cubed. So at least that's the point you're at. And without even knowing what the line is, you know the tangent line always looks like that. I mean, it's perpendicular. Or sorry, it's it follows the curve. So that's a pretty bad tangent line. Kind of bent there. And then the normal line is going to go this way, and they're perpendicular to each other. So at least we have the point, and now we need to know the slope. So sort of part A, a little bit of part C in there. Part B, you need to know the slope. So the slope formula is you take the derivative of the y and divide it by the derivative of the x, both with respect to time. And I gave you a little hint on that. This is 3 and then sine t squared. And then you multiply by the chain rule, so that's cosine. And then the bottom looks very similar, except it's going to be 3 cosine and then times minus sine. And so if you see, you can cancel the 3's, you can cancel a cosine, you can cancel a sine, and if you get this all down, it turns out to be nice and simple, just be tangent. And that's the slope formula. So before we do the second derivative, well, yeah, all right, we'll wait on a second. Second derivative is one that some people got, but it's got 2 parts. The denominator is just got a repeat of dx dt in the bottom. It's a weird formula, but you just got to look it up, I guess. You had the formula. So it's just a recopy of that. The top is the derivative of the previous derivative. So you take the derivative of tangent, it's secant squared. It's got a minus on it, so secant squared. And so you could have left it like that. If you wanted to, you could clean it up by combining these things, moving things to the top, whatever you want. But that's the concavity equation. Part C, the slope at pi over 4 is you just come back to the slope equation in part B, and the answer will be minus tangent of pi over 4, which is -1. And that makes complete sense because the line is slanted down and it's evenly slanted down, so pi over 4. So the line will be y minus, go back to the y coordinate, square root 2 over 2 cubed, equals the slope, -1 times x minus the square root of 2 over 2 cubed. And you can leave it like that if you want. If you try to simplify it out, you can. Some people simplified it out and got y equals x. And I'm like, really? Look at the picture. Okay, y equals minus x. No, that doesn't work either. So if you left it like that, I would be perfectly fine with that. And then part D is find the length. And actually, I told you the length, you just had to verify what it was. So part D, you just look up the formula. And it's the integral, and I gave you the bounds here, pi over 2. Then you just have to put the 2 derivatives in and square each one. And, anyway, so this is -3 cosine squared, sine squared is one of them, and the other is 3 sine squared, cosine squared, like that. And that gets you, a good chunk of it, and then just can you go from there? And so the rest is just algebra, pretty much. So we did square that. And again, and I said it in class a million times, and you've probably been told this a million times, and I don't know how to make you figure it out. If you square something that's negative, it cannot be negative. It just can't. So I don't know if other people need to mute here, but anyway, we square this out. We'll have 9 cosine to the 4th sine squared, 9 sine to the 4th. I don't know, Sean, you want to mute there? Whoever else isn't muted.
Why?
Or I'll do it for you. So it still looks kind of ugly. But the final step there was
One day I received a job offer from a low-level Hyperion programmer. Come to the moon, it said. Hunt a vault, be a hero. I didn't trust Hyperion, but I was too hungry.
There we go. I got it for you. So 9, and then you have cosine squared is in each term and sine squared is in each term. And if you factor it out, you'll have cosine squared plus sine squared. And, you know, this is, you got the integral set up and you got it through and you got down to a certain point and wasn't sure what to do. Do not take the square root of each piece and add them together. You got to quit making that mistake at some point in your life, I guess. You can't take the square root of 2 things added and then just add the square root. It just doesn't work. So that's equal to 1. That's the nice thing. So we'll just have the square root now is just 1 term, because this part all dropped out. So we'll have 3 cosine sine. Technically, you might have to worry about plus or minus, but everything is positive on this range, so you don't have to worry about absolute values or anything like that. And now you integrate that. I don't care how you do it. U equals sine, du equals cosine. Calc 2, just leave it at that. And you'll get 3 halves sine squared between 0 and 1, half, or pi over 2, half the time. So when you plug in those bounds, it'll be 3 halves minus 0, which is 3 halves. You were told in advance what the length was, and you just had to verify it. So setup and integration. And again, I'll post these solutions so you can go back through them if you need to study them for the final. 3, r equals 5 cosine theta. We did one, we may have even done this one, or certainly one that was really close to it. And it's just a circle. The radius is 2.5 because this is the full diameter to get 5. But that's that. I'm not sure what's going on with some of the other, either misinterpreting it. When you get, I mean, some people sort of drew something like that because you went to pi and the answer was -5, or -5. So that means you got to backtrack back over to here. So sort of you get this twice, you don't get this stuff on the other side. So just get that sort of figured out for the final, I guess. That's part A. Part B is area. So you look up the formula for area, and that's 1/2 your function squared. Now the bounds could be the tricky thing, but as you plot this, you realize you go 0, 90, and then back here, you'll get back to the beginning at pi, not 2 pi. So if you doubled that, you got twice the answer you should have. But anyway, also squaring the 5 is 25. So you get 25, which you can pull outside, cosine squared. Now, if you don't remember how to do that, well, you can look in the table. That's in the book. You can remember the trig identity for cosine. And in either case, the integral of cosine squared is theta over 2 plus the sine of 2 theta over 4. And 0 and 5. And so, you know, table, trig identity, something like that, double angle formula. So when you plug in pi, you'll get 25, you'll get pi over 2 for that one. You'll get 0 for the sine. And then when you plug 0 in and subtract, you also get 0. So 25 pi over 4. So we'll try that together. Which you already knew the answer, and that's why I didn't tell you just to do it. I had to verify it because this is a circle, so the area is pi r, which is 5 halves squared, and you also get 25 over 4 pi. So that's verification. And even the same thing on part C, find the length. And that's even easier because again, the length will be the integral, same bounds. If you doubled it, you got double the answer. And then it's r, which is 5 cosine theta squared, and the derivative, which is minus 5 sine theta squared, like that. So it's r and r prime, basically what it is. Again, if you squared this out and got minus 25, I don't know, knock it off. Be careful, it's a square. The parentheses are around the 5, so it's 25 cosine squared plus 25 sine squared. Got minus? Yeah, it's probably going to be impossible to do. So anyway, I could factor 25 out, and I'll get cosine squared plus sine squared, which is 1. So I'm just left with 25 on that one. And so that's 5 theta between 0 and pi, and plug in the boundary of pi. And that gives you the length, which you already knew the length, because it's the circumference. You could have figured it out that way. Let's see, x, what was it, r equals 5 cosine theta. And half the time, well, we didn't do too many, but some of the times we ended up multiplying both sides by r, and sometimes we squared both sides. And you could technically just try both. But the key is just cosine by itself without an r is annoying. So we want to get an r there, and so we multiply both sides by r. And in fact, it helps both sides. R squared and 5r cosine theta, because this first thing is just x squared plus y squared, and the other one is 5x. And you're done. You could clean it up, I guess, and get it down into a more standard form, but that's the deal. And then part E, every single time we did these, it was draw the picture. And I think maybe 3 of you did that. So learn the hard way. Draw the picture. You can't just set the curves equal to each other. It's not enough anymore. It won't work. You have to draw the picture. So we have the 2 curves, our original curve and then the new one. So the original curve, again, goes out here to 5. It is a circle. And the other one is one of these cardioids, which only goes out to 2, but at least just to maybe, this might be an exaggeration, but that's pretty close to what it looks like. So right off the bat, you can see I have 1, 2, 3 points of intersection, and points are the origin, which I already can see there, and now I got to figure out the other 2, and they look symmetric. So sort of when I get one, I can probably get the other. But the key is these must be listed as actual points, not just angles. So if you gave me the angle, that's not a point. So you need to find the point. So we need to find both r and theta for those points. And those do come from setting these 2 curves equal to each other. 5 cosine equals 1 plus cosine theta. So you have to solve that. So, I mean, you can see that you can subtract one of the cosines off, and then you'll get the cosine is a quarter. And then you need to find what theta is. And there's 2 answers for that. One is the arc cosine of a quarter, and that's the top one. But by symmetry, the angle is also negative the arc cotangent, or cosine, arc cosine of the quarter. You could either go up or you could go down, or you could, however you want to represent that point down And so then how do you get the actual R value out of that? Is you just plug it back in for the original. So if we sub back in, and might as well just sub it back into the first one. So our R value, and just look at it, it'll be 5 times the cosine of the arc cosine. And cosine and arc cosine are inverse functions of each other. So they'll cancel each other out, and we'll just have a quarter. Get 5/4. And that will be the 5/4, and the first angle is arc cosine quarter, and then the second one same distance out, so might as well just use 5/4, which you go down negative arc cos of that. And I think it's around 75 degrees or so. You know, if you want to put an approximation in there, we'll leave it like that. I can do the calculation there. Okay, so I'm not going to spend any more time on that this afternoon because we want to finish up this stuff and I'll see if you have questions. But that's the first test. I guess towards your grade is 14% of your grade. So you did really well. And if you didn't, well, you do have time to recover. I'm not going to curve the test at this point or anything like that. I got to see some improvement and trajectory. And if you show me some good trajectory, then I may weight the first test a little less, but not if it's just sort of, you know, if you don't make improvement along the way. On the final exam, it will be revisited, so you'll have a chance to reprove it. But, yeah. I won't say anything more. If you think I missed points or want me to regrade something, I'm happy to do that. But otherwise, let's get through 10.5 so you guys can then work on homework. There's a couple sections for tomorrow. They're not too long on dot and cross product, but still take time. Okay, so 10.5 is lines in space, lines in 3D. And this still holds for 2D, and we'll show how they connect. The new formulas connect with the old one. It's not going to be, you know, this is y equals mx plus b, or ax plus by equals c, or something like that, but lines in 3D are not going to work so well. Not as much as you expect. So let's just see here. Maybe I'll just do this one starting from an actual example. I'll grab a point here. I have one. Yeah, we'll make one up. So suppose I have a point in the plane or in the space, and so we'll just do 1, 2, 3. And we have another point. We could call it P1 and P2, but the book said, well, it's called the other point Q. So 1 minus 1, 1, something like that. These seem to be my go-to points here. So we still have the case that what determines a line? 2 points. If you have 2 points, even in 3D, 4D, whatever, you'll have only one line that goes through them. So we have this. So somehow we're in 3D. I'm not going to plot them, but you have P and you have Q, something maybe like that. And so there is only one line that passes, that goes through those. But what is the actual equation? Well, in 2D, what did you do for slope? It was like rise over rise. Or you just think about it, I go over and up. Well, it's pretty similar to that in 3D, except you don't just go over and up, you go out. So there's like a third component of the slope, and they don't call it the slope anymore. They say it's right at like this. D is the direction of the line. And it is a vector. So it basically tells me the rise, run, or I guess it's the run, the rise, and the out. Whatever the third one is called. So the direction is determined by, well, if you're going to go from any point on a line to another one, you know, how did you get there? Well, from P to Q, I didn't have to move at all. So I didn't have to do anything different P to Q. I just kept that same. 1 minus 1, basically. Now, what did I have to do to the second component to get from the part of P to the second part of Q? Well, I had to go from 2 to -1. So I had to subtract 3 off to get to there. And then what did I have to do from P to Q in the Z component? I had to go from 3 to 1, so I had to subtract that off. So in the picture, if I came over here and I actually drew the D vector there, that means the run is 0, the rise is -3, and the in and out board there is -2. So that kind of plays the role of the slope. It's the direction vector. And if you want, I think the book also says you can call this like PQ, right? So it's a reminder that that's from P to Q. So the equation of that line has 3 different forms for it. The equation of the line that I've drawn. Well, one of them is you can write like this. Kind of write it as a vector here. It is this vector here. And you think about it, how you do it in 2D is you pick a point, you go over and up and draw another point. And you go over and up and then you draw another point, and you go over and up and you draw another point, you just connect all those points. And by connecting them, that means it's every multiple of that slope. I could go over half of the run and up half the rise, and I'll still be on there. So the way this is written is I will have my point, my base point as they call it, and you can use either point because there's nothing specific about a base point on the line. But I'm going to start at 1, 2, 3. And if I had one copy of D, I go over 0, up -3, and out -2, I would hit Q. But if I did it again, go the run of 0, a rise of -3, and an out of -2, I would hit the next one. So I'd have 2 copies of D or 3 copies of D. If I wanted to get anything back the other direction, I would go negative copies of D. If I wanted to go things in the middle, I take half of D, or a third of D, or a quarter of D. Any multiple of D would give me points that are in the middle. So I use T as my multiple, or my parameter, the fancy word for it. And T is going to be it's going to have range from -infinity to infinity. And if I let every copy of D added on to P, I'll hit every single point. So I will have 0 T, just for emphasis, -3 copies of T and -2 copies of T in the Z direction. And that's the equation of the line in vector format. It's not real pretty, but there isn't going to be a y equals mx plus b anymore for a line. It's not going to work. We have this third component that I'm not, the pain to deal with. So that is one version. It's the vector form of your line. That's the vector form. You have what's called the parametric form, which says, let's just set these things to x, y, and z, but you have to keep it in a system of equations. So now you kind of have 3 things going on. Is you would say x equals 1 plus 0t. So x is never going to change. It's always going to be 1. Y is going to start at 2, but every time you do a t, it's going to get subtracted by 2, 3, subtracted by 3, subtracted by 2. And then z will be 3 minus 2t. And so you could write it like that. And that's, they call that the parametric form of a line. And if I had been more careful, I don't know if I can fit it in. I suppose I could if I got rid of this, but I'm going to get rid of it. That's right. Just so it's sort of all on one slide. What I could do, and this is kind of sneaky, is I could say, well, look, why do I have to write T, T, T over and over? I could just write it like this, where x is equal to 1. X will always be equal to 1. But let's solve for t in each of these last 2 equations. And since they're the same t, let's just set them equal to each other. So what do I get if I solve for t in the second equation? I'll get y minus 2 divided by negative 3. So move the 2 over and divide by negative 3. And that'll be t. How about in the last equation? I want to solve for t. I bring the 3 over, so subtract 3 and divide by negative 2. And that will also be t. So this is equal to t, and this is also equal to t. So I'll do z minus 3 over negative 2. But since that's equal to t and that's equal to t, it turns out you can just say, well, they're equal to each other. And I don't even have to write t at all. I just have to write x is 1, and these two things always have to be the same. No matter what y is, I could get z. No matter what z is, I could get y. And I don't even have to worry about t anymore. And so that's called the symmetric form. For the equation of the line. So you can either write it as a vector form, which kind of makes sense. You just follow this b as many times as you need to in either direction. This says to figure out x, y, and z. You start at the point 1, 2, 3, and then you add multiples of t for rise, run, and out. And then this one's kind of the trickier one, but x is always 1 on any point on that line, and you can figure out what y and z are simultaneously. If you use z, you can find y and vice versa. So it's not super satisfactory comparatively, but you know, what are you going to do? Back in 2D, you can do exactly the same thing, and let's make sure that this all works here. So let's pick 2 points, 0, negative 1, and Q is, say, 2, 3. So we can draw this one a lot nicer. So what's the equation of this line? And we can now write, we'll be excited, like 5 different versions of the equation, depending on which thing you need. So let's see. We'll just go to this now, it's just in 2D. So the first point here is at negative 1. That's P. 0, negative 1. Q is up here. And so we're interested in the line that goes through that. So that's L. So what's the equation of that line? Well, we're going to do it in 3 ways and show how it all ties back into the stuff that you already know of y equals mx plus b. So the first thing we do is we get the direction vector, which is just the vector from P to Q. So the vector that points from one point to the other. So you look at what you have to do. What do I need to do to get from P to Q? Well, I need to, x has to go up by 2, and y has to go up by 4. So to go from 0 to 2, I have to go up by 2, and to go up from negative 1 to 3, I got to go up by 4. And so that'll be the vector that points from P to Q. So if I just follow that, over 2, up 4, over 2, up 4, over 2, up 4, over 2, up 4, I'll get the entire line. And back the other way. Back 2, down 4, back 2, down 4, back 2, down 4. And all multiples in between. So instead of going too far, I could go 1, 2, and that would be halfway in between. Anyway, so let's see. The vector form is, well, I start at 0, and I add 2 copies of t, because I'm adding copies of this vector onto my base point. So 0, so the x component is 0 and 2t. The y component is negative 1 and 4t. And that's the vector form for my equation of the line. You don't have to write the 0, but it's in there for reference. The parametric form for the line is just to pull out the x and y and list them together. And after a while, you're like, this is annoying, I can just write it. But you still have to know that this means that the first one is x, so 0 plus 2t, and the second one is y, negative 1 plus 4. So you could write it like that. To get the symmetric form, which actually helps us lead back to the y equals mx plus b form, is solve for t in the first one, solve for t in the second one, and then just set them equal to each other. So if I solve for t in the first one, that'll be x minus 0 divided by 2. Then we don't have to write the 0. And then solve in the other one for t, you would add 1 to the other side, and you would divide it by 4. And that's the symmetric form of the line. Now, if you compare this against the stuff against the stuff you already know, one of them is the point slope form of the line, which is, well, let's use the point 0 minus 1. There's our point. Our slope is, well, what is our slope? The rise is 4, and the run is 2. So rise over run, 4 over 2 is 2. So the point slope form of the line will be y minus a minus 1 equals 2 times x minus 0. That's the point slope form of the line. The slope intercept form, well, we really can just take this guy and solve it out. So let's see, that's y plus 1 equals 2x. So we get y equals 2x minus 1. So 1, 2, 3, 4, 5 different versions of the line. And you might notice it, look at this symmetric one here. It compares really well. What happens if we multiply both sides by 4? Well, if you multiply this by 4, then the 2 and the 4 will cancel and just get 2x on that side. What happens if I multiply this by 4? Well, the 4s will just cancel, and I'll get y plus 1. You're like, oh yeah, look at that. These are exactly the same. So in 2D, all this like symmetric, parametric vector stuff all condenses down into just y equals mx plus b, or y minus y1 equals mx minus x1. Any of those slope forms. It does not work in 3D, unfortunately, but oh well. That's what we have to deal with. Okay, so before we do maybe a couple other examples, one last thing that we're going to want to know is suppose we have a line here and we have a point up here which is not on the line. Then the question is how far away is the point from the line? So this is called the point to line formula. And it'll work in 2D. Probably in 2D it may not be too difficult. In 3D it gets a little bit trickier because you gotta turn your brain in a certain way. So let's see how this works. So if we have a line in 3D and 2D and whatever, it doesn't matter, then what we can do is we can pick a point. I'm going to reuse the letters here, unfortunately, but I'm going to pick a point P, and I know that automatically from my equation of the line, I'm going to have a vector D which points that direction. I also, if I connect up here, I could draw this thing right here, and unfortunately the book uses, you know, Q, sometimes it's on the line, sometimes it's not on the line. I don't know, blame Hartman again. So this is the vector PQ from here to here. And anytime you do that, you've got the line and you've got this vector, it'll form an angle between them right there. So if you use basic trigonometry, maybe instead of calling this question mark, I'm going to call it H. I want to know what that height is. Then basically what I can do is I can just do, you know, basic trigonometry. If I knew the length of this line, which I do, for the segment here, it's the length of PQ, times I want the sine of the angle. So the height would be exactly the length of the vector from P to Q, so basically the distance this way. Then I'm going to project it down onto this one and take the sine of the angle in between. So that's the angle between D and PQ. So that's what that angle is there. The angle between the vector D and the vector PQ. So it's a basic triangle, so you just use the sine formula for that. But then again, the question is yeah, but how do I find the angle? What is the sine of the angle? It's all well and good if I knew the sine, it would be easy to do. I just multiply and I got it. But what is the sine? So turns out, this was something I just gave, but it turns out that the sine of the angle, so this is the formula that I at least wrote down, is that the sine of the angle between two vectors is equal to the length of the cross product. That's one of the examples why we did the cross product, divided by each length multiplied together. So length of PQ and length of D. So that's a nice formula that comes out of cross products, is you can get the sine of the angle between them. So if you put all that stuff together, here's what you get. The distance from any point to a nearby line is just, well, let's stick that in. What happens if we stick in sine? I'll have, the top will be the length of PQ cross D. And then what else do I have? I've got PQ on the top, but I have PQ on the bottom as well. So when I stick that sine in, that PQ length and that PQ length will cancel each other out. And all I'm going to be left with is the length of D. And so that's a pretty simple formula. If you knew D and P and Q, boom, you can find the distance from there. So I'm going to try an example here. So for example, let's suppose that this is my line in vector form. So 1 plus 2t negative 1 plus 3t and 1 plus t. And here's the point Q, 1, 1, 3, for example. So we want to find the distance from the line to the point. That's not a vector yet. So the distance from the line to the point. And anytime we do this, this distance means, yeah, it means the perpendicular distance, the shortest distance. So we've got a line, we've got Q sitting out here. We want to draw a perpendicular to our line and then just find that distance there. Okay, so I'm going to use the formula that I just had on the previous page. So I need a point that's on the line. And in this form, it turns out we're just backtracking what we just did. It's one point that's on the line is, I can just plug in t equals 0, and I will, so this particular point corresponds to when t is 0. I'll get the point 1 minus 1, 1. So it'll be exactly the numbers that are sitting in there. If I don't want to use that point, I can plug in any other value of t, and I would get another point that's on the line. If I plugged in 1, this would be 3, this would be 2, this would be 2. So 3, 2, 2 is another point that's on that line. So there is P. So I could figure out the vector from P to Q by just saying how much do I need to add to each component to get from P to Q. So here's P is 1, this Q is 1, so I don't need to add anything in the X component to get to that point. What do I need to do for y? Well, this key is starting at -1, but I need to get over to 2. So I need to add 2 to the y component. For the last one here, I need to get from 1 to 3. So I need to add another 2. So if I took this point, followed this vector, I would end up at Q, which is exactly the point. The direction of the line is what's being scaled and added on. So this 2, 3, and 1 is telling me my run, my rise, and my z direction, whatever you want to call that. And if you can pull those pieces of information out of the equations of the line, go back and forth between the two, that's the practice. But if you can, then it turns out that the distance that I'm looking for from Q to the line is just the length of the, I have to find the cross product of those two things, and then length it, and then divide by the length of D. And that'll give it to you. So that's what we're gonna do. One of those is easy, find the length of D. So that's square, 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 add them up, square root. So 4, 9, 1, add them up, that's 14, and then take a square root. So the length of the vector is just square root 14. For the cross product, I might need to come over here and do it. PQ cross B in that order. It may not actually matter because I'm going to do the length. So it doesn't matter if it's pointing one direction or the other. Just be careful. I can do this determinant as 0, 2, 2, 2, 3, 1. So, this kind of thing, it's like you haven't had a chance for your brain to digest it if you haven't seen it. We did it in the morning. Now we're doing it in the afternoon, and you have to master it. But here we go. So remember, in the I direction, you use this little determinant down here at the bottom. 2, 1, 3, 2. So 2 times 1, 3 times 2, and then you subtract. So it's 2 times 1 minus 3 times 2. So that'll be -4. For J, there's a built-in negative in this formula for determinant. Cross out everything, and you'll have 0, 2, 2, and 1. So 0 and 1 get multiplied together. The 2 and the 2 get multiplied together, and they get subtracted off. So minus 2 times 2. And then similarly for the K, this is back to plus. I look at these numbers when I cross out the K information. So 0, 3, 2 and 2, and they get subtracted off. So 0 times 3 minus 2 times 2. So if I did that all correct, that should be minus 4i minus a minus, so 4j and minus 4k. So put that off this side there. And now we have to do the length of that. So we grab that vector, we come over here and we do the length. That's the square root of -4 squared, so positive 16, positive 16, positive 16. So 16 plus 16 plus 16, 48. We'll get the square root of 48 over the square root of 14. And I suppose if you wanted to clean it up, there's really not much you can do other than to factor out a 16, take the square root and get 4 root 3 over root 14. Not very pretty, but it's around 1.8-ish. Kind of hard to see what's going on in space anyway. But it's interpreting the line using the formula appropriately, finding PQ, finding the correct cross product, and then computing that. So try to keep the afternoon ones section short as possible. I will try and do that. I know it's been a long day. But that really is section 10.5, and it's repeats of this sort of thing, maybe comparing lines, trying to figure out if two lines cross. You need to just draw a bunch of points and try and figure out these systems of equations. So I'm going to let you work on that. And if you have questions on any of those, we can handle it tomorrow morning. And with that in mind, I'm just going to open it up to see if you have questions about any homework, any problems you come across. Actually, let's do this. We'll take a quick 5-minute break. If you don't need any help and you just want to go work on the homework, peel out and go get to work, and I'll see you again bright and early tomorrow. And whoever's here in 5 minutes, when I come back, we'll do some homework problems. So that is the plan.